we've submitted our drafts, and I'm making my way through them. I've probably done about a quarter or maybe a third. So you'll be getting feedback over the next few days. And so it's a good time for us to do central limit theorem because this is a fat exercise and this is an important exercise as well. So hopefully we're just dedicating all of today's lesson to the exercise rather than making changes to our assignment prior to getting feedback. So central limit theorem. Now it's going to be important for us to read through these points, and because then when we get to the questions, we're going to be jumping back and saying, I remember what it said back here. Okay, so the first box there is pretty similar to what we did in exercise 9A. It's just talking about sampling distributions. The only thing, so we've got, suppose X is a random variable, which is not necessarily normally distributed. X has a mean, mu, and standard deviation sigma, so it's not necessarily normal. However, for sufficiently large n, that's going to be the notation we use. The distribution of the sample xn, so the distribution of the sample will be xn of size n is approximately normal with mean, mu, and standard deviation sigma divided by square root of n. So the larger n gets, the more normal the distribution of xn will be. So a couple of notes to make out. We know many texts suggest a rule of thumb such as n larger than 30. So our textbook does use this. They say if n's larger than 30, then it's suitable. Now, when we justify it, that is never a justification. We don't say n larger than 30, we say n is sufficiently large, okay? If n observations are chosen without replacement from a finite population, then n must also be compared. Yep, okay, so it's just talking about how, so that one's not really important. If x, okay, the third dot point is very important. If the variable is normally distributed, then xn will be normally distributed regardless of the value of n. And the same applies for the distribution of Sn. And then we have a summary of the properties there. So we've got the distribution Sn, we've got the distribution of xn, and then the mean and standard deviation, and then the last two dot points, what I just said before. If x is normally distributed, xn and Sn are normally distributed. If x is not normal, xn and Sn will be normal, provided n is sufficiently large. That's the words we'll use, and the assumption being n greater than 30. Okay, so let's get straight into the question then. We've got, suppose x is a random variable. It has a mean of 30 and a standard deviation of 10. Part A, is x 35 normal? The answer is going to be yes, because n is sufficiently large. Okay? N is sufficiently large if it's larger than 30. We don't reference the number 30, we just make the ambiguous statement, n is sufficiently large. Part B, find the mean and standard deviation of x35. So we look up in the top box. The mean of xn is the mean of x. All right. So the mean of x35, and we'll denote it like this: mean of x35 is the mean of x, which is in our circumstance 30. Okay. The standard deviation of x35 is the standard deviation of x divided by the square root of n. So in our circumstance, that's going to be 10 divided by the square root of 35. So we've found the mean and the standard deviation of x35. Part C, find the probability of x35 being larger than 32. Okay? So we've got this distribution x35. It's approximately normal because n is sufficiently large, and it has a mean of 30 and a standard deviation of 10 on root 35. And we're saying, what's the probability of it being larger than 32? Okay, what's this area under the curve? This is just a normal distribution calculation. Okay, so NCD, our lower boundary is 32, our upper boundary infinity. Our standard deviation is 10 on root 35 because we're talking about the distribution of x35. And our mean is 30. So that's the information that we're going to put in. So 32 to infinity, 10 on root 35, and 30. Good. Something wrong there. 32 to, oh yeah, no, that's right. Sorry, I've drawn 32 in the wrong spot. This is 30, and 32 is up here somewhere, isn't it? So that means our probability is going to be less than 50%. I've got 0.118. So let's write it like this. X 35 being larger than 32, 0.118. 3, 0.118. So 4 figures, round the fourth figure, we get 3 figures. Now, what we're talking about with the central limit theorem here is that as n increases, normality increases. And so that's exhibited by, flick back just one page and look at these bell curves, okay? As n increases, the bell curve becomes closer and closer to the mean. And of course that's going to be true because as our number of observations increases, all right, this n value is getting larger and larger and larger, which means we're dividing by a larger amount, so our standard deviation is getting smaller and smaller and smaller. So if the standard deviation is getting smaller, the results are closing in around the mean. They're getting closer and closer to the mean. Okay, good. So that's part C. Part D. Is x6 approximately normal? Okay. We have to see the distribution of x is not necessarily normal. It doesn't say anything about normal in the question. And so x6 is not sufficiently large because it's not larger than 30. Therefore, we cannot assume that the variable x6 is normal. So no, as n is not sufficiently large. Very good. Okay, so this kind of like ambiguous language being deliberate about, because there isn't a hard and fast rule as to what value of n constitutes sufficiently large, because it does depend on the normality of x itself. So we just use larger than 30, right? And we make the ambiguous statement. Okay, let's move on to question 2. I'm going to do that here because we don't need much room for question 2. All right, we've got x is a new variable. We're introduced to a new variable, and we're told this variable x is normally distributed, and it has a mean of 10 and a standard deviation of 3. Okay, part A says, is x4 normal? The answer is yes. If x is normal, then xn is normal for any n. All right, so that's the last dot point, the third dot point in our second box there. If x is normal, xn and sn are normal for any value of n. In the first question, x was not normal, and so that's why it did depend on the size of n. In the second question, x is normal, so it doesn't matter the size of n, xn is normal. Yes. Yes. And it's not because n is sufficiently large. x4 is normal because x is normal. Is x4 normal? Yes. So hang on, how can I write this? Is x4 normal? Yes, because x is normal. Okay, so that's the third dot point. If x is normal, xn will be normal. That's part A. Part B. How about S5, the sum of 5 observations? Well, again, appealing to that third dot point, if x is normal, xn and sn are normal. So S5 is also normal because x is normal. X is normal because x is normal. Okay, so that's what's going on with question 2. Very good. So here you're probably sort of wondering, how can we have distributions that aren't necessarily normal? There's plenty. And so now this next question is going to allow us to get into those kinds of weeds and to really demonstrate the central limit theorem here. All right, the price of smartphone apps have a mean of 89 cents and a standard deviation of $2.42. Now, the price of smartphone apps are not normally distributed. In fact, you'll find lots of them are very cheap. They follow like a Pareto distribution, right? Lots of them are very cheap, and a few of them are quite expensive. Okay, most of them are $1, Christina, $2, $3, but then some of them, like some smartphone apps, you can spend $60 on a smartphone app. Okay, so they're not normally distributed. That's why they have this odd mean and standard deviation. Interpret the variable x50. x50 is the distribution that arises from randomly selecting 50 smartphone apps. Okay? x50 is the distribution that arises from randomly selecting 50 smartphone apps. So we've interpreted the variable x50. Randomly selecting 50 smartphone apps. We've got two histograms shown below. One of them shows the variable x, and one of them shows the variable x50. So I'm going to provide an approximate sketch for both histograms. So there's one that's like this, and there's one that's like this. Okay. Now, what have we really tried to emphasize? As n increases, normality increases. So as n gets larger, the distribution becomes more normal. So one of these is very clearly the distribution of x, and one of them is very clearly the distribution x50. All right? This one is x50 because it's approximately normal. Okay? It approximately has a bell-shaped curve. This one is obviously the variable x. Like I said, we have lots of smartphone apps. Okay? The number that are cheap is very high. The number that are expensive is very low. So it follows this is a Pareto distribution. Okay, so we have the variable x and the variable x50. And interpreting those kind of histograms, that's a very common exam question, like it pops up like 50% of the time. And all you need to know is the one with the higher number is the one that's more bell-shaped. Okay? All right, I'm going to clear a space for question 4. And we've got question 5 as well. So question 4, this is where the central limit theorem pops out. Carlton Dry Stubbies. Okay, so they're a type of beer. They're normally distributed with a mean of 335 mils and a standard deviation of 5 mils. So this phenomena is normally distributed, right? And we've got the mean is 335 milliliters, and the standard deviation is 5. Okay. Part A says, find the probability of x, the distribution of x being larger than 340. Okay, what's the distribution of x? This is a randomly selected bottle of Carlton Dry, having a volume larger than 340. Well, we've got the mean, we've got the standard deviation. This is just an NCD calculation. Our lower boundary is 340, our upper boundary is infinity. Standard deviation and mean. Our standard deviation is 5, our mean is 335. This is all we're calculating for part A. All right, it's just a normal distribution calculation. So 340, infinity, 5, 335. 0.1586. This corresponds with, it's one standard deviation above the mean anyway. 159. Okay, so that's part A. Part B, a carton. So that's where you buy a whole slab, a box of Carlton Dry Stubbies, has 24 beers in it. Find the mean and standard deviation of x24. Well, the mean of x24 is equal to the mean of x. Remember? Okay, which is 335. But the standard deviation of x24 is the standard deviation of x divided by the square root of n, which is 5 divided by the square root of 24. It has a lower standard deviation. The results are compressing about the mean. Okay, so here's where the big difference is. Find the probability of x24 being larger than 340. Okay, so we're performing almost the same calculation, except there's a subtle difference, isn't there? What's the difference between here and here? The standard deviation is different. The standard deviation is smaller. So let's put that in. So we've got the lower, the upper, lower 340, upper infinity. Standard deviation is 5 on the square root of 24. And the mean is 335. So I'll put that in and let's evaluate this. I've got a feeling it's going to be low. 340 to infinity, and we're just going 5 divided by square root of 24. 4.816 times 10 to the minus 7. So minus 7, that means 7 zeros. Put the decimal after the first zero, and then we've got 482. Look at the difference there. What is going on? Why are these calculations so different? Here it is. I'm going to describe it verbally, articulate it, and then I'll write it up. In part A, we found the probability that one randomly selected bottle of Carlton Dry had a volume larger than 340. So if we're just randomly selecting one, we've got a probability of 0.16. In part B, we're finding the probability that the average volume of a whole carton, every single beer in the carton added together, divided by 24, is larger than 340. Okay, so that being the key difference. Like you can see how the probability compounds. It's very, very, very unlikely to get all of them together, 24 beers having a volume larger than 340. It's much more likely to just have randomly pick one. Okay? Because here we have a result above the mean, and here we have a result, 24 results having an average above the mean. Okay? So we'll have another example that lays out this same difference between. Let's describe it anyway. It does say, why is it different from A? So part A is the probability of a random, I won't rush, I'll write it up properly. Part A is the probability. And that's part C, isn't it? Part C. Part A, probability that a randomly selected bottle larger than 340. Part B, a randomly selected carton has an average volume larger than 340. It's appealing to every single one added together divided by 24. Alright, so I'll let you guys write it up and I'll just rub out the stuff around it. Okay, on to the next one now. People still scribbling? I'm just a fast writer. Make up for it with messiness though, hey?
That's not too bad.
Not too bad?
I've got someone sitting there just like riding half the time.
Yeah, he's worse.
Well,
Say it loudly, it's on camera.
well, you can tell what it is. It's just sometimes you just gotta
A
look
bit
at
of
it twice.
bit of guesswork involved.
Yep.
Same here, although I've said that out loud, so maybe that helps. All right. So, tins of Heinz spaghetti. This is our new random variable. Beer and spaghetti, they go well together. Tins of Heinz spaghetti are normally distributed with a mean weight of 420 and a standard deviation of 12 grams. A box contains 40 cans. So you're working in the supermarket, you've got to stack the shelves, you've got 40 cans in one box. Part A says, find the mean and standard deviation of the variable S40 and explain what it means. Okay, so the variable S40 is obtained by taking 40 observations of a can of beans and adding them together. A can of spaghetti and adding it together. So the mean of S40 is equal to n times the mean of x, which in our circumstance is 40 times the mean of x, and the mean of x is 420 grams. All right, so what's that? 16,800. And the standard deviation of Sn is equal to the square root of n times the standard deviation of x. So that's the square root of 40 times 12. 12 root of 40, I'll just leave as. Yeah. Okay, so we found the mean and standard deviation of the variable S40. Explain what it means in the context of the problem. Okay, well, we're told a box has 40 cans, and we've taken the weight of a can and multiplied it by 40, and the standard deviation and multiplied it by the square root of 40. So this variable here, S40, is what we expect the average weight of a box to be, and the standard deviation of the box of tin spaghetti. So S40 is the distribution of boxes of Heinz spaghetti. Is S40 approximately normal? The answer is yes. So that's still A. The answer is yes, not because n is sufficiently large, but because x is normal. If x is normal, then xn and sn are normal for any value. Yes, as x is normal. All right, we're told that the tins of Heinz spaghetti are normally distributed. Therefore, we put them in a box. The weight of the box is also going to be normally distributed. And then part C, we have a box is too heavy for strongman if it weighs more than 17 kilos. Determine the probability that the box will be too heavy for strongman. So what we're saying here then is, what's the probability of a box, that is the variable S40, being larger than 17,000 grams? Okay? Got to make sure we're consistent with the unit here, right? And so this is just a normal distribution calculation. Lower, upper, standard deviation, mean. And we're talking about 17,000 grams to infinity, standard deviation of 12 root 40, and a mean of 16,800. Let's evaluate that. Again, just like when we did the BCD calculations, it's not necessary to notate this. Like, you don't get marks for it, but it's helpful for checking, going back and checking your working out. I'd encourage you to do it. Or the other way to do it, as we've seen with BCD, is like this: NCD, lower, upper, standard deviation, mean. You can put that in your calculator like that as well. So you don't have to notate it, but I encourage you to, and you'll see me do it as well in solutions, so I can communicate how I've arrived at certain answers. Okay, so let's evaluate this, unless someone's done it already. We've got 17,000 to infinity, 12 root 40, and 16,800. 4.24 times 10 to the minus 3. Alright, I said minus 3, that's 3 zeros. Put the decimal after the first zero, and then those figures.
204.
2. Thank you, Lauren. Okay, so this is a big chunky exercise. We'll work through them all. I've gone into a lot of detail here, really trying to emphasize the difference between the variable x and the variable xn. Okay, the variable sn and the variable x. All right. So let's have a go at this exercise, see how you go with it. Yeah, good luck.